Hello and welcome to lecture 29 of the course Theory of Computation. We have been seeing Turing machines. So far we have seen the basic model of Turing machine, which is a deterministic Turing machine with a single tape. Now we will see other variants of Turing machines. In this lecture we will see multi-tape Turing machines. So what are multi-tape Turing machines? It's just what you would imagine the name suggests. Instead of a single tape, we will have multiple tapes. So like what we have here, you have one state control and you could have multiple tapes, and with each tape containing different possible contents. And the heads of each of these tapes do not have to move in the same manner. Like in each step of computation, the tape 1 the head could move right, the tape 2 head could move left, and tape 3 the head could, like, based on whatever the rules are. The rules allow each head to can allow each head to make in a different direction, right? So it's like a Turing machine, but instead of a single tape, it can have multiple tapes, and for each tape there will be a head. So one thing that I would like to note here is that in the basic model, in the single tape Turing machine, we had a state control and we had a tape and a head, and the only options that we allowed was left and right for the movements of the head. In this case, we are going to allow one more option, which is the stay option. So the tape head is also allowed to stay. This is because in the case of a single tape, there is nothing that gets accomplished by allowing a certain head to stay or the head to stay, because if you stay at the same spot, you may stay there for some time, but eventually you will have to move. So if you stay there for 3 moves and finally you write a 1 in that location and you move, so you might as well have written a 1 in the first instance itself and then made the move. There was nothing gained by staying in the same place for a while, because it's not really like furthering or progressing the computation. Whereas in the case of multi-tape Turing machine, the stay option becomes meaningful, because you could have maybe the move is in such a way that in the first tape the head has to move to the right side, and in the second tape also the head has to move to the left side, and in the third tape we just want the head to stay wherever it was. So this is a right, this is a left, and this is a stay, and we want this option because we don't necessarily want each head to move in all the moves. We may want only subset of the heads to move. So that is why a stay option becomes meaningful in the case of a multi-tape Turing machine, right? Because we want to allow the possibility of a head remaining in the same place, because some other head may be moving. In the case of single tape Turing machine, if we allow that possibility, it means that there is no progress in the computation, because there is only one head, and that head remains staying put or remaining in the same place means that the computation can progress only when that head moves, right? So that's why in the case of a single tape Turing machine we did not allow the stay option, whereas here it makes sense to include the stay option. So let's just see the definition. So I won't get to the detailed definition, but I'll just say the brief definition, only highlight the differences. So we have the Turing machine being the 7 tuple, q sigma delta, q sigma gamma delta, q0 being the start state, q accept and q reject, qa and qr. And so in the case of a single tape Turing machine, we had the transition function transition function was q cross gamma going to q cross gamma cross left right. So basically you are at a certain state, you read the tape content at that position where the head is pointing, and then you have to decide which state to go to, what to write on the tape. So which state to go to is this q, what to write is this gamma, and then left or right, whether the tape head should move to the left or the right. Here it's exactly, or it's very similar here, but here notice that instead of one tape, we are allowing k number of tapes. So there could be multiple tapes. So in the figure here, k is 3. There are 3 tapes here, right? So here k is 3. So the moves will be decided based on the current state and what all the tape heads read. So here it would be decided based on what the tape head, all the 3 tape heads read. So that's why we have gamma power k right here. So based on all the k tape heads, what they read, and then we have to decide which state to move to, what to write on all the k tapes, right? And LRS, so here I have already explained the meaning or why we need the stay option, and each of the tape heads we have to say whether they move left, right or stay. So that is the main difference. So first of all, this gamma and this LR, they become k-fold, and the second difference is that in addition to L and R, we allow a stay option. These are the 2 differences. So the delta is of this form: delta Qi A1, A2 up to Ak, meaning these are the tape contents that you read. Qi is the current state, A1, A2 up to Ak, and then Qj is the next state. Then you say B1, B2, Bk be the symbols that you write, and LR etc. be the movements that you make. So maybe just to see an example, maybe I'll just erase this and we'll see an example. So let's say delta, so here it is state is Q5, C is the first tape, C is the second symbol, and in fact C is the third symbol coincidentally, and let's say this was delta Q10. Let me just checking if there is a worked out example. No, Q10 A, B, C, L, S, R. Okay, so what I am saying is, if this is the situation, then you move to Q10. Okay, the first tape you write A. So A, B. It was the head was pointing at C. So now this becomes A. The second tape you write B, so it was pointing at C, so it becomes B, D, B, C, B. The other wherever the head was not pointing, those symbols are not changed. And the third tape, it was pointing at C, and that remains C. So you have A, C, B, B. Wherever the head was not pointing, that does not change. And further, the first tape moves one step to the left, right? The second head stays, and the third head moves one step to the right. So this is how one move of the Turing machine will look like, of a 3-tape Turing machine would look like, right? So sometimes having multiple tapes affords us some conveniences, in the sense that because you may have to read something which is on the one end of the tape, but now this allows some kind of convenience in terms of the memory organization, right? So by having multiple heads, and it allows us to organize things more efficiently, and this can make the algorithm simpler, right? So let's see one simple example. So remember we had this language in the previous, this is something similar. We had this language in the previous lecture, A power I, B power J, C power K, where we said that I multiplied by J equal to K, right? So now if we have to somehow accomplish that, let's say, so how it happens is usually that the input is in the first tape, the entire input, and then we use the other tapes as some kind of a working tapes. So suppose this was the entire input, A power I, B power J, C power K. Suppose it was in tape 1. We can read the input and then copy it, let's say some parts into second and third tapes, or how many ever tapes there are. And let's say we got to this situation, right? So let's say right now we are in this situation. So the A's are in tape 1, B's are in tape 2, C's are in tape 3. Okay. So now we can operate this tape in the operate this Turing machine in the following manner. You strike off one A from here, and for one B here, one C here, one B here, one C here, and so on. And we can work in a manner similar to the previous algorithm that we had earlier described, right? But because it is in separate tapes, it becomes simpler, because earlier we had the entire thing in one tape. So you had to come back to the right, then see the A's, then go back to the left to cross off the C's, and so on. But when we have things in separate tapes, this going back and forth can be avoided. So, and this can result in some time savings as well, right? So for each A, we strike a B, we strike a C, we strike a B. So the algorithm is pretty much the same. At the end, we remove the A's. Sorry, we uncross the B's, and then again we strike the next A. Sorry, we strike the next A, and then again strike a B, strike a C, strike a B, strike a C, strike a B, and so on, right? And if at any point B's remain but C's do not remain, we reject. If at any point B's are struck out but C's, or if everything else is struck out but C's remain, even then we reject. Right? So these are the two cases where we reject. If at the end C's are remaining, you reject. And if we don't have C's, we have struck off B but we are looking for C's but that are not there, even then you reject. Otherwise, if everything matches up at the end, you accept. Right? So this, I'm not elaborating it because we have seen the same language in the previous lecture. So the algorithm is the same, just that this helps us avoiding this multiple back and forth things, because if it's in different places, different tapes, so it's organized better. So in the 3-tape machine, it's easier to check if the input is of this form, right? A power I, B power J, C power K, where K is I times J. So mostly what we see here is that there is some convenience that is afforded. Now the natural question is, suppose we have 3 tapes, or suppose we have 10 tapes, suppose we have big number of tapes. Clearly whatever we do, like you can just work it as a single tape machine, because you could just completely decide to not use any of the remaining tapes and work everything in the first tape. So meaning, what I mean to say is, if you have a 10 tape machine, I could just focus on the one tape and kind of ignore the remaining space. So what I'm trying to say is that a K tape machine is at least as powerful as a 1 tape machine. Right? A 10 tape machine is at least as powerful as a 1 tape machine. Natural question to ask is, does it give us more power? Meaning, are there languages that K tape machine can recognize that a 1 tape machine cannot, or a 3 tape machine can recognize that a 1 tape machine cannot? And the answer is, as I have written in this slide, the answer is no. Meaning, K tape model seems more powerful, but whatever a K tape machine can do, a 1 tape machine can also do. Every multi-tape machine is equivalent to a single tape machine, right? And the idea is fairly simple. So let's see what the idea is. The idea is basically, if you have K tapes, you try to compress all that information into 1 tape. Basically encode, so you write everything in 1 tape. This naturally means that you will have to do more back and forth, which is unavoidable, but that is pretty much all that you will have to do. So let us see. Right. So suppose, I'll just pictorially represent a 3 tape machine. Okay. So you have Qi being the state, and there are 3 tapes. The first tape contains ABC, AB. The second tape contains 101, and the third tape contains AAB. The first tape, the head is in the third location, second tape second location, third tape first location. So what you can do is to encode it in the following way. So basically we encode the entire thing into, this is the encoding. So encode into a single tape, and these hash symbols are delimiters. So hash are the delimiters, meaning these symbols that I am going to highlight just now are going to separate or tell us where each tape content is ending and the next tape content is starting. Okay. So the first tape content that you see here is ABCAB, and this is encoded between the first two hash symbols. After the second hash symbol, the contents of the second tape starts, it's 101. After the third hash symbol, it's AAB, okay, which is the content of the third tape. And finally, we include one more hash to show that we are that is the end of the contents of the third tape. Okay, so that is how we encode the contents. But there is also one more issue. The 3 tape machine has 3 heads, whereas a 1 tape machine has only 1 head. So we also have to find some way to kind of keep track of the various head movements. So the 3 tape machine, there are 3 heads, but a 1 tape machine has only 1 head. So how to encode the head positions? So what we do is we denote it in the tape itself. So we have the special symbols to kind of indicate the head position, right? So here C, the third symbol C contains the head, or the head is pointing at the third symbol of the first tape. So I denote it by C with a hat in the single tape conversion, right? So there is only one symbol in the part that corresponds to the first tape. This is the part that corresponds to the first tape. There is only one symbol with a hat, and that symbol is that symbol indicates where the tape head was in the 3 tape equivalent. And similarly, we have one symbol in the with a hat in the second tape, which is a 0, and one symbol with the hat in the third tape, which is the first A, right? So basically now our alphabet size has at least doubled, because I need all the original alphabet, all the things that were originally in the alphabet, which is gamma. The new tape alphabet also needs every symbol with a hat on it, because that needs, so now it is C with a hat, but the next time when the tape head moves to the right, I may need A with a hat, right? And similarly, second tape it is 0 with a hat, and the next time I may need 1 with a hat. So every symbol I also need the equivalent with a hat, right? And also I need the delimiters hash. So if the original alphabet was size 10, now I need an alphabet of size 21, but that's all that you need, right? It's not really a huge blow up. So what we do is, so now this is the situation of the Turing machine. So you represent everything into one tape, and then what you do is you move from left to right, and you have only k tapes, in this case 3 tapes. So you notice that in the first tape, the third location, the C, the tape head was pointing at C. Second tape, the tape head was pointing at 0, that you know because of the special symbol with the hat. And the third tape, A, has the tape head pointing at A. And then when you come to the end, you know you are at the end. So now you know that the first tape head looked at an C, second tape head looked at an 0, third tape head looked at an A. So now, and you know that the state was Qi. So now you can look at the rule. So what was, you can just ask what was delta Qi C0A, right? Now suppose this asked us to go to, let's say, something like Qj B1 B, maybe left, right? So suppose this is the rule of this tape. So first what we do is the head goes from left to right, understands what is represented, comes back to the left. So now it knows that it is in state Qi. C0A are the heads are pointing to C0A. Now it knows the rule of the original multitape Turing machine, right? So it knows the rule of the original multitape Turing machine. Now, which is now Qi, delta Qi C0A is delta Q is Qj B1B LLL. Now what that means is that I'm just trying to find some space to maybe I'll just do some rearrangement. Okay, and I'll just erase this. So now, so which means you go to state Qj. So this was Qi. which means now you go to state Qj. So you have hash. Now the first head you write a B here, so A, B, A, B, and then you moved left, so the head comes to the second position. Second tape head you write a 1, so you have 1, 1, 1, tape head moves left. And the third position, sorry, you don't have an A, but you have a B, B, A, B, and you moved left, but then from the leftmost position you cannot move further left, so this is what you have. So now you know this is the rule, and then you make another pass from left to right, and you implement this change in the single tape. So you move from left to right, you read where the heads are, then you come back to the left. You know the transition function of the original multi-tape Turing machine. You know what that is, so now you know the delta thing, right? So delta was QJB1B LLL. Now you make another pass from left to right and implement this, which is what we have done. So basically what we are doing is we are just making these multiple passes and implementing this. So every step of the Turing machine, of the multi-tape Turing machine, now I need to make, let's say, first left to right, then coming back to the left, then again left to right, then coming back to the left. So maybe like 4 moves that spans the entire tape length, right? So this is again same thing I have written here. So originally if the input is let's say W1 W, which is W1 to Wn. So originally the original starting configuration is the entire input is in the first tape, right, between the first and second hash, then every other tape is blank. Now you scan it from left to right. So you have k tapes, so the k plus 1 hash symbol indicates the end of the tapes. You remember the head positions. Now you know the rules of the multi-tape Turing machine, and you make a second pass, and you update this k virtual tapes. So basically it is like a virtual memory, right? So you have a single tape, but you have this k virtual tape locations where you are encoding it, right? And suppose in this case it didn't really happen, but suppose at some stage we need to make space, let's say in this tape position, maybe I'll highlight something. Let's say this B, or the third tape here, let's say third tape here, I wanted to, let's say, write B, A, B, B. Let's say I want to move one step to the right. So I need to move the hash and create space, but we do that. If that is required, we move the hash symbol and create a blank, and that's how we would implement a multi-tape Turing machine in a single tape. So basically it's a simulation, but it increases the running time, as you may guess, because earlier you could move the things in the single tape left right individually, but now every single move requires us to scan the entire tape from left to right multiple times, right? So that's how you would implement a multi-tape Turing machine using a single tape. And what this tells us is that anything that you can do with a multi-tape Turing machine can also be done with a single tape Turing machine, and the moves, the accept, reject, loop, everything exactly remains the same, right? So we didn't really change any functionality. Whatever input would have accepted would still remain accepted. Whatever was rejected would still be rejected. Whatever looped would still be looped, which means it's exactly equivalent. So if a language was Turing recognizable in a single tape model, it's also Turing recognizable in the multi-tape model, and vice versa. It's if and only if, because multi-tape is at least as powerful as single tape. That's easy to see, and in this proof we say that it is not any more powerful. So if it was the class of languages that are Turing recognizable by single tape is exactly the class of languages that are Turing recognizable by multi-tape. So nothing more, nothing less. Same for decidable. If a language was decidable in a multi-tape Turing machine, it is decidable in a single tape Turing machine as well. Same the other way also. So we'll later see other models also. In all these cases, we'll see that the definitions of recognizable and decidable, they are kind of robust. They don't really depend on these different models that we are defining, right? So in that sense it's good. So we don't have to qualify that this language is decidable for single tape machine and not for multi-tape. No, we don't have to do any of that. Recognizable means recognizable in single tape and multi-tape, or not recognizable in either model. Same for decidable. And that completes this lecture, lecture number 29, right? So we saw the multi-tape Turing machine model, and we saw how it computes, and we saw that it is not any more powerful than a single tape Turing machine. So the idea of this proof was that you can encode the contents of multiple tapes into a single tape. So single tape, using these delimiters and these hat symbols, we can kind of create virtual tapes in the single tape itself, right? And by sacrificing on the time, by making lots more moves left to the right, we are able to encode, or you are able to kind of reflect whatever happens in the multi-tape Turing machine in the single tape Turing machine. So that completes lecture 29. In the next lecture we will see another variant of Turing machine, which also will turn out to be equivalent, which will be the non-deterministic Turing machine. So that's it for lecture 29, and see you in lecture 30. Thank you.